The second geometric problem that calculus looks at is finding the area under a curve. And this is what we call integral calculus. Now, to give you an idea of what this means, finding the area under a curve, let's look at an example. So let's look at this example right here. The area between the curve y equals x and the x-axis over the interval 0, 1, the closed interval. Now what this is saying is, okay, so I'm going to draw this. And I want it over So what the question is asking is, what is this area in here? Now, you may be looking at that and saying, wow, that looks awfully like a right-angled triangle. This is kind of boring if it would be a right-angled triangle. And the answer is yes. Yes, it is a right-angled triangle. So we have the area, so there's the base times the height divided by 2. So in this case, it's 1 times 1 divided by 2 is 1/2. That sounds very interesting. You might be saying, so why do we need calculus? Okay, so this is a very simple problem that we know what the answer is for 1/2. And what I'm going to show you is a more complicated method that allows us to look at any curve. And what we can do is, the idea is to break this up into rectangles. Okay, so what we are going to do is So what we would like to do is we're going to split this up into, say, like n many rectangles. So we do this. Okay. So we have this area here. We can calculate the area of these rectangles. Okay, so we can approximate that. So let's say there's n many, but you're thinking to yourself, but I'm missing this area here. So it's not going to be a very accurate approximation. So what we need to do is try to have more and more rectangles. And by doing that, then we can get a much more accurate approximation of it. So that if I have much more smaller rectangles, you can see that that area that I'm not counting anymore in the green is getting smaller and smaller and smaller every time I make thinner and thinner and increase the number of rectangles in it. So you notice that the area here, kind of our error, is getting smaller and smaller as I increase the number of rectangles. So how do we do that? Well, what we do is we initially start off with dividing it by n many rectangles. So let's just call this our arbitrary rectangle right here. So it will have a width. And so this width is called our delta x. And in this case, our interval we have from 0 to 1. So we will go from, we're looking at the entire interval, so we have 1 minus 0 divided by n many rectangles gives us the width of 1 over n. Okay. And then what if I wanted to pick a point? I wanted to pick a point for the rectangle. Well, it will be, here's one point here, here's a second point here, 2, 3, 4, all the way up to the nth rectangle. So there would be 1, 2, 3, all the way up to n many rectangles. So if I wanted, say, f at my first point, say x1, well, that would be right at the very beginning. So I would use 0 divided by n. If I did my second point, well, that would be kind of the first point. And there's n many of them. Because again, this is just a straight line. So that's giving my value at this third point, the first, second, and third. Well, that would be 2 divided by n. All the way up to, and then I'll have f at x, n. So that would be n over n. Okay. So like I said, we can approximate this. We have an approximation of f at x, 1. We'll have delta x, which is the width. So we have our height. In this case, for the very first rectangle, there's 0. So it's 0 times the width plus x2, f at x, 2. Then we'll have delta x. So there it is. For this second rectangle, there's our second point. And then so we multiply by that height, multiply by that width, which is our delta x. And we do the same thing all the way to f at x of n delta x. Okay, so that's just an approximation. But we can make this get really close to the true value by taking it to the limit. And how can we do that? By, again, making the number of rectangles, the number of n, go to infinity, that we have infinitely many rectangles, which means that we'll be adding more and more and more and more, so that that area, that we're not counting in that green area gets really, really small. It goes to 0. So it means that we're approaching the true area under the curve. So that means that we have a equals, and we'll take the limit as n goes to infinity of f at x at 1 delta x, f at x 2 delta x, and so on and so forth until we get to f at x n delta x. Okay, so what I'm going to do is I'm going to actually now substitute my values in for f at x at 1, which we know is 0n, and the delta x is 1 over n plus the next one that I have is 1 over n multiplied by 1 over n plus 2 over n multiplied by 1 over n all the way down to now I kind of noticed this. If I have n rectangles, I think what I should have is, if I'm starting at 0, I should have it n minus 1. So I have n minus 1 divided by n multiplied by 1 over n. Okay. So I notice that I have a factor of n squared in each of them. So I'm going to pull that out. So now I'm left with 0 plus 1 plus 2 plus all the way up to n minus 1. Well, since we have a 0, I'm just going to kind of ignore that. So I got n squared. 1 plus 2 all the way up to n minus 1. Now recall that we did before the sum of 1 plus 2 plus all the way up to n is equal to n plus n times n plus 1 divided by 2. So in this case, we're going to have 1 plus 2 plus all the way up to n minus 1. So what does that equal? Well, that means that we're going to have it that equals n minus 1 n divided by 2. Okay, so I can do the same thing here. The limit as n goes to infinity, 1 over n squared. And I can substitute that value in now for this summation here. So I have n times n minus 1 divided by 2. Starting to get a little bit more manageable. So now again, the limit as n goes to infinity of 1 over n squared. And I'm going to expand that out so that I have n squared minus n divided by 2. So that's equal to the limit as n goes to infinity of, so I have n squared divided by 2n squared minus, then I have n divided by 2n squared. Okay, so don't panic. We can definitely still do this. And okay, so the n squared divided by 2n squared. So the n squareds cancel. So now I'm just left with 1/2 minus, now I have 1 over 2n. Okay. We're almost done. What I'm going to do is I can apply the limit to each individual term here. So I have the limit as n goes to infinity of 1/2 minus the limit as n goes to infinity of 1 over 2n. Now, as n goes to infinity, it doesn't affect this 1/2 here. So that's just equal to 1/2 minus, this is the interesting part. So the limit as n goes to infinity of 1 over 2n. So you look at this as a fraction. So as n gets really big, what happens? Well, as n gets really big, it means the denominator gets really, really big. So that's, if you put in n equals 1, so that's 1/2. And then 2, so then you, for n equals 2, you get 4. If you put in 3, you get 1 over 6. So what you're seeing is that this fraction is going to get really, really small if you make n really, really big. So that goes to 0. So after all of that, the area is equal to 1/2, which is what we had anticipated at the very beginning when we had used this straight line, that it's the area of a rectangle, that the area is equal to base times height divided by 2 is equal to 1/2. And what we did was we broke these up into rectangles, and if we let there be an infinitely many number of rectangles, it means that this green area here gets really, 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 really small as the number of rectangles gets really, really large. And that we have our approximation, it goes to the true area if we take it to the limit. And doing all that mathematics, all that algebraic manipulation to get to that point that the area is equal to 1/2. Now you might be thinking, wow, that was a lot of work to show what I already know for the area of a rectangle. Yes, that's true. But the question then that I have to ask you then is what if you have a different kind of curve? What happens if I give you a parabola now? And now I ask you, what's the area under that curve of y equals x squared? You don't have a formula now to calculate that from elementary mathematics. We don't have, this is clearly it's not a triangle anymore. So what calculus would do is we can approximate this using, say, n equal width rectangles And we would let the number of rectangles approach the infinite. And as we do that, the area between that we're not counting gets really, really small, which then gets really close to the true value of the area under x squared. We'll do that in the next video.